Our universe operates by two rulebooks that fiercely disagree. The infinitely small world of particles follows the bizarre laws of quantum mechanics. The grand cosmic stage of stars and galaxies obeys Einstein's elegant theory of gravity. For a century, physicists have searched for a single master law, a theory of quantum gravity that can make these two rulebooks one. By the end of this exploration, you will understand 30 of the most daring attempts to rewrite reality's deepest code. We will see theories where space is woven from loops, where reality is a hologram, and where time itself might be an illusion. Is our smooth cosmos actually built from a frothing quantum foam? The answer will change everything we know. What feels more real to you, the solid ground beneath your feet or the invisible quantum links that might truly hold it all together? The search for that master law begins with a radical idea. What if space itself is not smooth and continuous, but is instead woven from threads? This is the startling vision of loop quantum gravity. Forget the empty stage of Einstein's universe. In this theory, the fabric of reality is a tapestry of unimaginably tiny, vibrating loops. These loops are the smallest possible units of space, like individual stitches in a cosmic cloth. They link together to form a vast dynamic network physicists call a spin network. In this quantized geometry, nothing is infinitely divisible. Just as you cannot have half an electron, you cannot have half a unit of space. Area and volume come in tiny, discrete packets, a pixelation of reality at the smallest scales. This solves a core problem of the Big Bang. In Einstein's equations, the beginning of everything is a mathematical point of infinite density, a singularity where the laws of physics break down. Loop quantum gravity erases this terrifying infinity. As you rewind the cosmos, gravity becomes so powerfully repulsive at these tiny scales that the universe cannot crush itself to nothing. Instead, it rebounds. The Big Bang was not a beginning from nothing, but a big bounce from a previous era of collapse. Our entire cosmic history could be one cycle in an endless, breathing rhythm of expansion and contraction. It is a universe built not from emptiness, but from a shimmering web of connections. But if space is woven from loops, what are the threads themselves made of? This question leads us to the most celebrated and controversial candidate in the quest for quantum gravity, string theory. Its core idea is a beautiful and profound shift. Forget dots. The fundamental ingredients of reality are not zero-dimensional points, but unimaginably small, one-dimensional filaments, vibrating strings. Their size is almost impossible to grasp, about 100 billion times smaller than an atomic nucleus. In this symphony of the cosmos, every distinct note played by a string corresponds to a different particle. One specific vibration gives you an electron, another creates a quark, and a third, crucially, produces the particle that carries the force of gravity itself, the hypothetical graviton. For the first time, gravity is not forced into the quantum world. It emerges from it naturally, as just another melody in the vibrational spectrum. Yet this elegant vision demands a radical reimagining of the cosmic stage. To produce all the notes in nature's symphony, the strings need more room to vibrate than our familiar 3 dimensions of space and one of time can provide. String theory requires extra dimensions, often 6 or 7 of them, curled up into shapes so tiny we never perceive them, like the intricate folds of a carpet viewed from a great height. This framework is not a single theory but a family of them, with names like Type 1, Type 2a, Type 2b, and heterotic, each with its own mathematical quirks and vibrational rules. Its ultimate ambition is staggering: to be a true theory of everything, a single mathematical structure from which all particles and all forces, including gravity, inevitably arise. It promises a universe where every star, every atom, and every law is written in the harmonics of vibrating strings. Is our reality the physical expression of a hidden cosmic music? String theory's hidden dimensions are a mathematical necessity, but what if we could watch space and time being built from the ground up? Causal dynamical triangulations offers a radically different, computer-friendly blueprint for reality. This theory takes a bottom-up, almost architectural approach. It discards the idea of a pre-existing, smooth stage altogether. Instead, it proposes that the fabric of spacetime is assembled from the simplest possible geometric shapes, tiny triangular blocks called simplices. Think of them as the cosmic equivalent of Lego bricks. These blocks are not just randomly glued together. They must follow one ironclad rule: causality. Each connection must respect a clear before and after, ensuring time always has a direction and cause always precedes effect. This rule prevents the quantum foam from becoming a chaotic, timeless jumble. In powerful computer simulations, physicists perform a staggering sum over histories. They let the program combine trillions upon trillions of these tiny causal blocks in every possible configuration, following the quantum principle that every potential path contributes to reality. The result is nothing short of magical. From this frenetic, churning quantum soup of simple shapes, a smooth, four-dimensional universe crystallizes. The familiar dimensions of space and the relentless arrow of time are not input into the equations, they are the output. They emerge large and stable from the collective behavior of these microscopic, timeless pieces. It is a profound demonstration of how the orderly cosmos we experience could be a statistical miracle, born from quantum chaos. This provides one of the most compelling links ever simulated between the discrete, pixelated quantum world and the continuous, classical reality we call home. The architecture of spacetime may not require extra dimensions or vibrating strings. Another powerful idea suggests gravity itself can be tamed by its own quantum nature in a framework known as asymptotic safety. This approach is both elegant and deeply pragmatic. It asks a simple question: what if we could treat gravity like every other force in nature? The strong nuclear force, electromagnetism, they are all described by quantum field theories, mathematical frameworks that have proven spectacularly successful. Why should gravity be the stubborn exception? The core challenge has always been a problem of infinities. In conventional attempts to quantize gravity, calculations at extremely small scales tend to blow up, producing meaningless infinite results that break the theory. Asymptotic safety proposes a brilliant escape route. Imagine a map of all possible theories of gravity, a vast landscape where every point represents a different set of rules for how gravity behaves at different energy scales. As you zoom into higher and higher energies, approaching the furious intensity of the Planck scale, these rules flow and change. The revolutionary idea is that this flow could converge on a special fixed point. Think of it as a whirlpool in the river of possible theories. No matter where you start on the river, the current pulls you toward this stable center. At this asymptotic fixed point, the strength of gravity's quantum interaction stops changing and becomes constant or safe. This stability is the key. It would cut off the vicious infinities, making the mathematics perfectly well-behaved and predictable. Gravity would become a consistent quantum field theory in its own right, described purely by the geometry of spacetime itself, the metric, without needing any exotic new ingredients. It is a minimalist dream, a way to make the universe's most familiar yet enigmatic force finally play by the quantum rules. Could the solution to our greatest cosmic puzzle be hidden in the graceful flow of gravity's own equations? The idea of a universe built from simple causal links takes an even more minimalist form. Causal-set-theory proposes that the deepest foundation of reality is not geometry, not strings, but pure causality itself. It strips spacetime down to its most essential ingredient, the simple, unbreakable relationship between cause and effect. In this view, the cosmos is a vast collection of discrete, indivisible events like grains of sand. These are the fundamental points of reality. They are not placed in a pre-existing space or time. Instead, they are connected only by a single binary relation, a causal link. One point either precedes another or it does not. This creates a vast, shimmering network of before and after relationships, a cosmic web of causality called a causal set. From this sparse, elegant structure, everything else must emerge. The smooth, continuous spacetime of our experience, with its definite distances and clear dimensions, is not fundamental. It is a secondary, approximate picture. Think of it like a photograph in a newspaper. Up close, you see it is just a collection of discrete black and white dots. But from a distance, those dots blend seamlessly into an image with shape, depth, and meaning. In the same way, the familiar four-dimensional continuum of our lives emerges from the collective pattern of countless causal links. The flow of time is not an illusion here. It is woven into the very fabric of the theory from the start, because the network of causes inherently defines a direction. This is a universe where the sequence of events is more real than the space between them. Could it be that distance is merely a story told by causality? Gravity feels so fundamental, the very force that sculpts galaxies and pins us to the planet. But what if it is not a force at all? What if gravity is merely a side effect, an illusion born from something more primitive? This is the radical proposition of entropic gravity, also called emergent gravity. In this view, gravity is not fundamental like electromagnetism. It is emergent like temperature or pressure. You cannot find a single atom of temperature in a room. It is a collective property of countless molecules in motion. Proponents like physicist Eric Verland argue gravity is the same, a statistical consequence of something deeper, information. At the heart of this idea is entropy, a measure of disorder or, more profoundly, of hidden information. Verland suggests that what we perceive as gravity is actually a force that arises when the entropy, or information content, of spacetime changes due to the presence of matter. Think of empty space as a calm, uniform sea of microscopic degrees of freedom, like an immense, quiet memory bank. When you place a mass like a star into this sea, it disturbs the information pattern. The entropy in the space around the mass wants to increase to reach its maximum possible disorder. This tendency for entropy to increase creates an effective force that pulls other objects toward the mass. A beautiful analogy is a polymer, a long chain-like molecule. When you heat it up, its entropy increases and it stretches out into a more disordered configuration. In entropic gravity, spacetime itself behaves like an elastic medium. A mass does not pull on other objects through a mysterious force. Instead, it creates a gradient in the entropy of space, and other objects move along that gradient, much like the polymer stretches toward a state of higher disorder. This is not just a philosophical shift, it makes a stunning observational prediction. Verland's equations suggest that the observed motions of stars within galaxies, which we currently attribute to the gravitational pull of invisible dark matter, might simply be the result of this entropic effect. The extra force we measure could be an emergent phenomenon of the quantum information of spacetime itself, not the pull of unseen particles. Could the greatest mystery in modern cosmology, dark matter, be solved not by finding a new particle, but by realizing that gravity itself is telling us a different story? The idea that gravity might be an illusion leads to an even more astonishing possibility. Perhaps our entire three-dimensional reality is one as well. This is the holographic principle, a concept so profound it redefines the nature of information and existence. It proposes that all the information needed to describe everything within a given volume of space, every star, every atom, every event, can be perfectly encoded on its two-dimensional boundary. Our rich three-dimensional world would be a holographic projection from a flat, two-dimensional surface, much like the three-dimensional image on your credit card emerges from a flat, etched film. The seeds of this idea were planted in the fiery logic of black holes. When matter falls into a black hole, it seems to vanish, destroying information, which violates a core quantum rule. Physicist Jacob Bekenstein and later Stephen Hawking discovered that a black hole's entropy, which measures its hidden information, is proportional not to its volume, but to the area of its event horizon, its surface. The information content of a black hole is painted on its skin. Gerard T. Hooft and Leonard Susskind took this breathtaking leap, suggesting that if it is true for the most extreme objects in the universe, it must be true for all of space. Reality itself might be pixelated, with a fundamental limit to how much information any region can contain, and that limit is set by its surface area, not its volume. The full mathematical realization of this principle is the anti-de Sitter conformal field theory correspondence, often called the greatest gift of string theory to physics. It establishes a precise one-to-one dictionary. On one side of this duality is a universe with gravity, described by string theory, living in a special, negatively curved space called anti-de Sitter space. On the other side is a completely different, gravity-free quantum theory, living on the flat, lower-dimensional boundary of that space. These are not two descriptions of the same thing. They are mathematically proven to be the same thing. A complex gravitational event, like two black holes colliding in the bulk of that universe, is exactly equivalent to a specific, turbulent interaction of quantum particles on the distant boundary screen. This means the force of gravity and the very dimensions of space could be emergent phenomena, generated from the complex quantum entanglement of particles living on a lower dimensional surface. Are we and everything we see just a magnificent shadow play cast from the edge of the world? If reality is a holographic projection, what is the screen itself made of? At the very smallest scales, the screen might not even be a smooth surface. Non-commutative geometry proposes that the fabric of spacetime is woven from a strange, quantum logic where the very concept of a point breaks down. In our everyday world, measurements are simple and orderly. If you drive 5 miles east, then 5 miles north, you end up at the same spot as if you drove 5 miles north first, then 5 miles east. The operations commute, the order does not matter. But in the quantum realm, this familiar certainty vanishes. For particles, measuring position first and momentum second does not give the same result as the reverse order. This is the famous Heisenberg uncertainty principle, built into the mathematics of non-commuting variables. Now, apply this radical idea not to particles, but to the stage they perform on. Non-commutative geometry suggests that at the Planck scale, the coordinates of spacetime themselves do not commute. Measuring a location in one direction and then another might yield a different result than measuring them in the opposite sequence. This means spacetime points lose their precise identity. You cannot pin down an event to a single, infinitesimal dot. Instead, spacetime becomes inherently fuzzy, a kind of quantum foam where the very notion of here and now is blurred by a fundamental uncertainty. This is not a defect but a feature of a deeper, more elegant geometry. Pioneered by mathematician Elaine Connes, this framework uses a sophisticated new mathematical language to describe this fuzzy landscape. In this geometry, the familiar continuum of points is replaced by algebraic structures where coordinates are represented by operators that do not commute, much like the matrices in quantum mechanics. The stunning power of this approach is its unifying potential. Connes and his collaborators have shown that the entire standard model of particle physics, with all its forces and particles, can be derived naturally from the spectral properties of this non-commutative spacetime. The Higgs field, the electromagnetic force, the weak and strong nuclear forces, they all emerge as inevitable geometric consequences of this fuzzy quantum structure. In this view, general relativity and the standard model are not two separate theories forced together. They are two different perspectives on the same underlying non-commutative geometry. The force of gravity is the curvature of this fuzzy space, while the other forces are the internal twists and fluctuations within it. It is a vision where the laws of physics are not written on spacetime, but are the very shape of spacetime itself once we learn to see its profoundly quantum nature. Could the universe be built not from points, but from a web of uncertain relationships? The fuzziness of spacetime at its smallest scales demands a new language, one that might not even use points as its alphabet. Roger Penrose offered a breathtakingly different vocabulary with twistor theory. Forget building reality from tiny dots in a void. Penrose's vision proposes that the true fundamental objects are twistors, complex mathematical entities that exist in a higher dimensional abstract space. In this radical reframing, the events of our familiar four-dimensional spacetime are not primary. They are secondary constructions derived from the intersections of lines in this twistor space. A single twistor represents not a location but an entire light ray, a complete history of a particle moving at the speed of light. When these twistor lines intersect, they define a point where an event can occur in our spacetime. It is a profound shift in perspective, like describing a movie not by each individual frame, but by the complete story arcs of all its characters. The intersections of their journeys create the plot. This geometric elegance yields remarkable power, particularly in simplifying the fiendishly complex mathematics of particle scattering. Calculations that are monstrously difficult in traditional quantum field theory can become astonishingly simple and visually intuitive in the twistor picture. The tangled webs of particle interactions unravel into elegant geometric patterns. This has forged deep, unexpected connections between quantum theory and the geometry of spacetime itself, suggesting that the quantum properties of particles and the structure of the cosmos might be two sides of the same twistor coin. It is a perspective that does not quantize gravity, but instead seeks a realm more fundamental than spacetime, from which both quantum mechanics and gravity naturally emerge. Could the universe be a shadow cast not from a flat screen, but from the intricate geometry of a higher dimensional light? The search for a deeper language of reality often circles back to a single profound question. What are the ultimate atoms of space? Group field theory offers a startling answer, one that builds on the loops of quantum gravity but takes the idea into a new, abstract dimension. Imagine the fundamental entities of the cosmos are not tiny loops existing in space, but rather abstract quantum fields that exist prior to space itself. These are not fields in the universe, they are the fields from which the universe is woven. In group field theory, or GFT, the basic ingredients are quantum fields defined not over points in space, but over mathematical groups which encode possible geometries and connections. Think of each basic excitation of this field as a tiny chunk of geometry, a quantum of space like a single droplet. These droplets, these quanta, are the same kind of building blocks you find in loop quantum gravity's spin networks. But here is the revolutionary shift. Group field theory treats these quanta of space like particles in a more familiar quantum field theory, like electrons in the quantum field of electromagnetism. This is called second quantization. It allows for the creation and annihilation of space itself. In this picture, empty space is not a silent void. It is a boiling sea, a quantum vacuum teeming with fleeting, virtual quanta of geometry popping in and out of existence. Our smooth, classical universe emerges only when a vast number of these fundamental quanta undergo a phase transition. They condense, locking together into a coherent collective state. This is the cosmic analogy to molecules condensing from a gas into a liquid. The individual molecules are still there, but their collective behavior creates an entirely new substance with new properties like fluidity and waves. In the same way, the abstract quanta of group field theory condense. Their intricate patterns of entanglement and interaction crystallize into what we perceive as the continuous, four-dimensional fabric of spacetime and its gravitational field. Geometry is not assumed, it is born from this condensation. This framework provides a powerful bridge to another approach, the spin foam models, which describe the possible histories of spin networks as they evolve. Group field theory can be seen as the overarching quantum field theory that generates these spin foam histories, summing over all the possible ways spacetime can quantum leap from one configuration to another. It suggests that the stage of reality is not a given, but a dynamic, emergent performance, an ocean of geometric possibility that has frozen into the familiar world around us. What we call the universe may be just one possible condensate in a sea of quantum geometric potential. The condensation of space from a quantum soup leads to an even more radical origin story. Quantum gravity proposes that the newborn universe possessed no space or time as we know them at all. Instead, it began as a formless, chaotic network, a graph of pure connection. Picture an unimaginably dense, hot web where every single fundamental node is connected to every other. In this primordial state, there is no distance, no direction, no geometry. It is pure relationship, a seething tangle of links with no underlying stage. Then, as this fiery network of existence expanded and cooled, a cosmic phase transition occurred like water freezing into ice. The highly connected links in the graph began to break. As they did, a remarkable structure crystallized. Most links froze out, leaving behind a sparser network where only nearby nodes remained connected. It is from this sparse, orderly pattern that the very concepts of locality and dimension emerge. The way nodes connect defines who is a neighbor and who is distant. In certain configurations, this frozen graph naturally gives rise to a lattice that behaves like a three-dimensional space with time. Our entire four-dimensional continuum is not fundamental. It is a low-energy illusion, a frozen pattern in a deeper graph of quantum relationships. This elegant freezing process could solve two profound cosmic puzzles. First, the stunning uniformity of the cosmic microwave background, the afterglow of the Big Bang. In standard cosmology, points on opposite sides of the sky were never in contact, yet they glow at exactly the same temperature. Quantum gravity offers a beautiful explanation. In the initial hot, maximally connected state, every point was in direct contact with every other. They were neighbors on the graph. This primordial intimacy allowed them to reach a uniform temperature before the links broke and space as we know it expanded, locking that uniformity into the sky we see today. Second, it could explain the origin of Lorentz invariance, the principle that the laws of physics are the same for all observers moving at constant speed. This symmetry is a cornerstone of Einstein's relativity, but where does it come from? In quantum gravity, it is not a fundamental law written into the universe's code. It is an emergent symmetry, a pattern that naturally arises as the graph freezes into its stable, low-energy state, much like the perfect hexagonal symmetry of a snowflake emerges from the chaotic process of freezing. Our smooth, relativistic spacetime, then, is not the starting point of physics. It is the quiet, cold aftermath of a graph's great thaw. But a frozen graph is not the only way to break the symmetry of the cosmos. A bold and controversial theory suggests we must break something even more fundamental, the sacred symmetry between space and time itself. This is Horava-Lifshitz gravity, named for physicist Peter Horava, who proposed it in 2009. Its premise is radical. What if the stubborn problems of quantum gravity stem from treating time exactly like a dimension of space? Einstein's relativity weaves them together into a single, unbreakable fabric, spacetime. But Horava dared to ask, what if that union is only a low-energy truce? At the highest energies, in the ultraviolet frenzy of the early universe, time and space might split. In this theory, they scale differently, a property called anisotropic scaling. Time is given a privileged role, allowing gravity's equations to be reshaped in a way that tames the vicious infinities that plague other approaches. By sacrificing Lorentz invariance, the principle that the laws of physics look the same to all uniformly moving observers at these extreme scales, Horava-Lifshitz gravity becomes renormalizable. This technical term simply means the mathematics stays finite and sensible at all scales, a crucial hurdle that Einstein's original theory fails to clear. It is a trade, surrendering a cherished symmetry to gain a workable quantum theory. The consequences of this split are profound. One of the greatest mysteries in modern cosmology is the accelerating expansion of the universe, which we currently attribute to a mysterious dark energy. Horava-Lifshitz gravity offers a dramatic alternative. The accelerated expansion might not need any dark energy at all. It could be a natural consequence of the modified gravitational equations when the universe is nearly empty, a geometric effect emerging from the theory's different treatment of time. This theory also paints a vivid new picture of the universe's infancy. Without the strictures of full Lorentz invariance, the early cosmos could have experienced exotic phases, like a period of superluminal expansion or dramatic gravitational waves, leaving distinct imprints on the cosmic microwave background or the distribution of galaxies. Even black holes are transformed. Their interiors and the nature of their singularities could be radically altered, potentially resolving the information paradox. Because it makes such stark, testable predictions that differ from Einstein's relativity, Horava-Lifshitz gravity is not just a mathematical exercise. It is a target for observation. Data from gravitational wave detectors, from precise maps of the cosmic microwave background, and from studies of the large-scale structure of the universe could one day reveal the subtle fingerprints of a cosmos where time and space were not always equal partners. Could the key to quantum gravity be a cosmic divorce between the dimensions we hold most dear? What if the universe's size is an illusion, a mere gauge with no physical meaning? This is the startling proposition of shape dynamics, a radical reformulation of Einstein's own theory that challenges our most basic intuitions. In general relativity, the theory is invariant under all smooth coordinate transformations, a principle called diffeomorphism invariance. This means the laws of physics look the same whether you describe the cosmos from Earth or from a spaceship spinning near a black hole. Shape dynamics makes a different, more restrictive trade. It gives up this full invariance for a powerful new symmetry, invariance under spatial conformal transformations. This is a fancy way of saying the theory cares only about the shapes of things, the angles between them, and not at all about their absolute sizes. In this view, stretching or shrinking the entire universe uniformly is not a physical change. It is just a change of description, like switching from miles to kilometers. The volume of the cosmos becomes unobservable, a mere mathematical convenience with no direct physical reality. What is real, what the theory fundamentally describes, are the conformal geometries, the shapes and angles that remain unchanged when everything is scaled up or down. This shift in perspective offers a profound new angle on one of the deepest puzzles in quantum gravity, the problem of time. In many approaches, time becomes frozen or ambiguous at the fundamental level. But in shape dynamics, a clear, global notion of time naturally emerges from the evolving shapes of the universe. Time is not an external parameter ticking away. It is the measure of change in the spatial conformal geometry. The universe ticks forward as its shape evolves, not as it grows. This provides a truly background-independent picture, where reality is not a story unfolding on a fixed stage of spacetime, but a dynamic, self-contained narrative of pure relational shape. Could it be that the cosmos is not expanding into anything, but is simply changing its shape in a way we misinterpret as growth? The search for quantum gravity is not just about building new theories. Sometimes it is about confronting a paradox so sharp it threatens to tear our understanding of reality apart. This is the black hole firewall paradox, a thought experiment that sets the three pillars of modern physics on a collision course. Imagine an astronaut, Alice, bravely falling toward a large black hole's event horizon. According to Einstein's equivalence principle, the cornerstone of general relativity, crossing this point of no return should be uneventful. There is no special surface, no wall of fire. For Alice, it is just empty space, a smooth continuation of her fall toward the singularity. But quantum mechanics and the holographic principle tell a very different story. The holographic principle insists that all information about what falls into the black hole is encoded on its event horizon. To preserve the purity of quantum information, this information must eventually be radiated back out as the black hole slowly evaporates via Hawking radiation. This creates an impossible conflict, for the information to be both inside the black hole with Alice and also encoded on the horizon for eventual release. The particles just inside and just outside the horizon must be entangled in a very specific, complex way. Yet, for the information to escape via Hawking radiation, the outgoing radiation particles must also be entangled with those same interior particles. A fundamental rule of quantum mechanics called monogamy of entanglement states that a single quantum particle cannot be maximally entangled with two different systems. It must choose. In 2012, physicists Olmary, Marolf, Polchinski, and Sully, known as AMPS, laid out this brutal choice. Either the entanglement is broken at the horizon, which by the rules of quantum mechanics releases an immense amount of energy, creating a literal wall of fire that incinerates Alice. Or the equivalence principle is wrong and the event horizon is a violently singular place. This is the firewall paradox. Resolving it forces us to question our deepest assumptions. Perhaps the principle of black hole complementarity is correct, suggesting that both stories are true from different, mutually exclusive viewpoints. Or perhaps our understanding of entanglement in curved spacetime is incomplete. The firewall is not just a puzzle about black holes. It is a glaring signal that our current laws are fundamentally incompatible. The true theory of quantum gravity must dissolve this paradox, showing us how information, geometry, and quantum entanglement weave together seamlessly at the universe's most extreme edge. The answer will rewrite not just the fate of a hypothetical astronaut, but the very rules of existence. The firewall paradox reveals a terrifying crack in reality's foundation, but a breathtaking conjecture offers a way to seal it. The ER equals EPR proposal, put forward by Juan Maldacena and Leonard Susskind, is a mind-melting bridge between the two greatest pillars of modern physics. It suggests that the spooky action at a distance of quantum entanglement is not just a link between particles, but the literal fabric of spacetime itself. To understand this, we must look at two ideas born decades apart. In 1935, Einstein, Podolsky, and Rosen, or EPR, published a famous paper highlighting the bizarre nature of quantum entanglement. They described how two particles could be created together, fly light years apart, and yet remain mysteriously connected. Measuring one instantly determines the state of the other, a connection that seems to defy the speed of light. That same year, Einstein and Nathan Rosen published another paper, this one on the geometry of gravity. They found a mathematical solution in general relativity that described a bridge connecting two distant regions of space, a structure we now call an Einstein-Rosen bridge or a wormhole. For decades, these were seen as separate, unrelated curiosities, one from the quantum world and one from the geometry of gravity. The ER equals EPR conjecture boldly states they are the same thing. The quantum entanglement between two particles, an EPR pair, is not just correlated with a microscopic wormhole, an ER bridge, linking them. They are two descriptions of a single, fundamental phenomenon. Entanglement is the quantum signature of a geometric connection. This turns our intuition inside out. We picture entangled particles as separate objects with an invisible thread between them. But if ER equals EPR is correct, that thread is not a metaphor. It is a physical, albeit incredibly tiny, tunnel through the geometry of spacetime. The particles are not far apart, they are directly connected through a hidden shortcut. This provides a stunning mechanism for the holographic principle. How can the information about a three-dimensional volume be perfectly encoded on its two-dimensional boundary? The answer may be a vast, dense network of quantum entanglement linking every point on that boundary. Each entangled pair is a microscopic wormhole stitch, sewing the interior bulk of space into existence from the connections on its edge. What we perceive as smooth, continuous space is the emergent geometry of an unimaginably complex web of quantum links. It suggests that without entanglement, spacetime would fall apart into disconnected fragments. The connectivity of the universe, the very fact that you can travel from here to there, is built from the spookiest phenomenon in quantum mechanics. Are the vast distances between stars merely an illusion, masking a universe woven together by a billion tiny threads? This vast web of entanglement stitching space together confronts a staggering numerical nightmare, arguably the worst prediction in the history of science. It is the cosmological constant problem, and its scale is almost impossible to comprehend. Our universe is expanding at an accelerating rate, driven by what physicists call dark energy. The simplest explanation for this dark energy is a cosmological constant, a tiny, persistent energy density inherent to the vacuum of space itself. The problem is not that this number is large, but that it is absurdly, impossibly small. According to the rules of quantum field theory, the vacuum is not empty. It is a seething, frothing sea of virtual particles constantly flickering in and out of existence. Every possible quantum field contributes a little energy to this background hum. When physicists sum up all these contributions from every known particle and force, they calculate a vacuum energy density. The result is a number so catastrophically large it should have ripped the universe apart in a fraction of a second after the Big Bang. Specifically, the theoretical prediction is about 10 to the power of 120 times larger than the tiny, gentle value we actually observe. That is a 1 followed by 120 zeros. To grasp this mismatch, imagine predicting the mass of the entire observable universe, but your calculation instead gives you the mass of a single proton. The error is not just wrong, it is off by a factor that dwarfs the number of atoms in the cosmos. This is not a minor adjustment, it is a screaming sign that our understanding of how gravity couples to the quantum vacuum is fundamentally, profoundly broken. Any viable theory of quantum gravity must solve this fine-tuning crisis. It must explain why the universe's vacuum energy is not just small, but precisely tuned to a value that allows galaxies, stars, and life to form. One controversial escape route is the anthropic principle within the vast landscape of string theory. In this multiverse scenario, our universe is one bubble in an infinite froth of universes, each with a randomly different value for the cosmological constant. We simply find ourselves in one of the exceedingly rare bubbles where the constant is small enough for structure to form. It is not fine-tuned for us, we are here because it was tuned just right. While logically consistent, this feels to many like a surrender, explaining away a calculation rather than fixing it. More active solutions seek to modify gravity itself. Ideas like degravitation propose that the vacuum energy might be large, but gravity somehow filters it out, becoming insensitive to this constant background hum over large scales. Massive gravity theories, which give the graviton particle a tiny mass, can also alter how spacetime responds to a cosmological constant, potentially screening its cataclysmic effects. These approaches try to tackle the problem head-on, suggesting that Einstein's equations need revision precisely in how they react to the energy of nothingness. The cosmological constant problem is a quiet, numerical scream from the heart of quantum gravity, a reminder that the empty space around us holds the deepest and most unresolved mystery of all. The quiet scream of the cosmological constant demands a radical answer. Could the solution be that gravity, unlike light, is not perfectly massless? This is the daring proposition of massive gravity, a theory that directly challenges one of the most sacred tenets of Einstein's relativity. In the standard picture, the force of gravity is carried by the hypothetical graviton, a particle that must be massless to ensure the force acts instantaneously across any distance, matching the precise predictions of general relativity. But what if the graviton has a tiny, almost imperceptible mass? The implications would shatter our cosmic understanding. A massive graviton would mean gravity behaves differently over immense scales. It could weaken over cosmic distances, potentially explaining the accelerating expansion of the universe without any need for dark energy. The attraction between galaxies would fade faster with distance than Einstein predicted, mimicking the effect of a mysterious repulsive force. For decades, this idea was considered mathematically doomed. Early attempts to give the graviton mass inevitably introduced ghostly instabilities, phantom fields with negative energy that would cause the vacuum of space to spontaneously decay, a clear sign of a flawed theory. It was a dead end until a breakthrough. In 2010, physicists Claudia de Ram, Gregory Gabadads, and Andrew Tolley achieved the seemingly impossible. They constructed a consistent, ghost-free theory of massive gravity, now known as the DRGT model. Their ingenious work found a way to give the graviton a mass while carefully cancelling out the deadly instabilities that had plagued all prior attempts. It was a triumph of theoretical craftsmanship, proving that a massive graviton could, in principle, exist within a sensible framework. The theory paints a new portrait of cosmic history. In the early, dense universe, the graviton's mass would have been irrelevant, and gravity would have behaved exactly as Einstein described, forging galaxies and stars. But as the universe expanded and thinned out, the mass would have begun to assert its influence, gradually altering the long-range pull of gravity and driving the observed acceleration. We are not seeing a new form of energy, but a modification of the oldest force. This is not just a theoretical fantasy, it is a testable hypothesis. If the graviton has mass, it would travel slightly slower than light, and gravitational waves would disperse, with different frequencies arriving at slightly different times. Precision observations from detectors like LIGO and Virgo are now searching for this subtle signature. Furthermore, the altered gravitational force would affect the orbits of stars within galaxies and the bending of light from distant quasars. By scrutinizing these cosmic motions, astronomers are placing ever tighter limits on how massive the graviton could possibly be. So far, it must be astonishingly light, but the hunt for its fingerprint is one of the most active frontiers in physics. The universe's acceleration might not be driven by an unknown energy, but by the quiet weight of gravity itself. A massive graviton is one way to bend the rules of gravity, but it is not the only path. Another compelling alternative suggests we need not invent dark matter at all, if we are simply willing to rewrite the equations of gravity on cosmic scales. This brings us to two powerful and often competing ideas, F of R gravity and modified Newtonian dynamics, or MND. They both start from the same stunning observation. When astronomers measure how fast stars orbit the centers of galaxies, they find a puzzle. The visible matter, the stars and glowing gas, does not provide enough gravitational pull to hold those stars in such swift orbits. According to Newton and Einstein, those stars should be flung out into the void. The dominant solution for decades has been dark matter, a vast halo of invisible particles providing the extra gravity. But F of R gravity and MND ask a radical question. What if the fault is not in our stars but in our laws? First, consider F of R gravity. This is not a single theory, but a rich class of possibilities that modify Einstein's general relativity in a specific, elegant way. In Einstein's original formulation, the core of the equations comes from the Einstein-Hilbert action, which depends linearly on the Ricci scalar, a single number that measures the curvature of spacetime at a point. In f of r gravity, this simple linear term is replaced by a function, f, of that Ricci scalar. This one change has profound consequences. The function can be crafted so that gravity behaves exactly as Einstein predicted in regions of high density and strong curvature, like near stars or black holes. But in the vast, low-density outskirts of galaxies where the curvature is gentle, the modified function can make gravity stronger. This extra gravitational kick in low-density regions could precisely mimic the effect of a dark matter halo, pulling stars around faster without any invisible particles. It is a geometric fix, changing how spacetime itself responds to matter in the cosmic quiet. Then there is MUND, which takes an even more direct and empirical approach. Proposed by physicist Mordechai Milgrom in the 1980s, MUND is a phenomenological adjustment to Newton's second law at extremely low accelerations. Milgrom noticed that the discrepancy in galaxy rotation curves always appeared when the gravitational acceleration fell below a specific, incredibly tiny threshold, about 100 billion times weaker than the gravity we feel on Earth. He proposed that in this regime, Newton's familiar law, force equals mass times acceleration, needs a modification. The acceleration itself is no longer proportional to the force in a simple linear way. Instead, it transitions to a new rule where the acceleration is proportional to the square root of the force. This subtle tweak has a dramatic effect. It predicts that in the faint outskirts of galaxies, orbital speeds become constant, exactly as observed, without invoking any dark matter. MUND has been remarkably successful at fitting the rotation curves of a vast array of galaxies with just one new constant, something dark matter models often struggle to do with the same simplicity. This creates a fascinating tension. Is the missing gravity due to a new ingredient in the universe, dark matter, or a new rule for an old force? The debate is fierce and ongoing. Crucially, these modified gravity theories are not necessarily rivals to a full theory of quantum gravity. They might be its low-energy offspring. Just as Newton's gravity emerges from Einstein's relativity in weak fields, a future quantum theory of gravity could naturally yield an effective description like f of r gravity, or even a MUND-like behavior in the appropriate limit. The true master law might predict subtle deviations from Einstein's equations on galactic scales that we are currently interpreting as dark matter. The quest to find these deviations is now a central drama in astronomy, with every new map of distant galaxies and every observation of colliding galaxy clusters serving as a test. Do we live in a universe filled with invisible mass, or one where gravity itself whispers a different law in the emptiness between the stars? The debate between dark matter and modified gravity forces us to examine the very foundations of our theories, revealing a deeper, more philosophical crisis. At the absolute core of canonical quantum gravity lies a mathematical statement so profound it seems to erase time itself. This is the Wheeler-DeWitt equation, the cornerstone of attempts to quantize Einstein's general relativity using the methods of quantum mechanics. It was derived by John Wheeler and Bryce DeWitt in the 1960s, and it presents a breathtaking yet deeply puzzling vision. The equation describes the quantum state of the entire cosmos, a single, static wave function of the universe. But here is the shocking part. The equation contains no time variable whatsoever. It is a timeless equation for a timeless state. The universe, in its most fundamental quantum description, simply is. It does not evolve, it does not change, it just exists frozen in an eternal now. This is the stark, undeniable problem of time. If the bedrock of reality is timeless, how do we, who are undeniably part of that reality, experience a relentless flowing time? Where does the past, present, and future come from? This is not a minor technical glitch. It is a conceptual chasm between the quantum description of the whole and our lived experience within it. One compelling interpretation suggests that time is not a fundamental ingredient, but an emergent property that arises from within the universe. Think of it like temperature. A single molecule does not have a temperature. Temperature is a collective property of countless molecules in motion. In the same way, a solitary, isolated universe has no external clock. But within that universe, different subsystems can interact. Time might emerge from the correlations between these parts. Imagine the universe as a vast, intricate clock. The hands of the clock, representing one subsystem like the position of planets, move in a correlated way with the internal mechanism, another subsystem like the expansion of space. We do not see an external time, we see one part of the clock changing relative to another. The flow of time is the story we tell by comparing the state of one thing to the state of another. A beautiful formalization of this idea is the Page-Wouters mechanism, proposed by physicists Don Page and William Wouters. They showed how a universe governed by a timeless Wheeler-DeWitt equation can contain internal clocks, like a simple harmonic oscillator or even a complex observer, that tick relative to the rest of the system. From the perspective of an internal observer using such a clock, the rest of the universe appears to evolve in a perfectly standard way with a clear past, present, and future. Yet, from the God's eye view of the entire wave function, nothing changes. All moments, all configurations are equally real and present. This suggests a block universe where time is an illusion of perspective, a way for a conscious subsystem within the whole to make sense of its place in the vast, static quantum tapestry. The problem of time forces us to ask, is time the most fundamental rhythm of existence, or merely the most personal story we tell ourselves? The timeless universe of the Wheeler-DeWitt equation presents a profound challenge, but how do we actually calculate the quantum behavior of this frozen cosmos? The answer lies in a powerful and beautiful extension of the loop quantum gravity framework, a concept known as spin foams. If the universe's geometry is a tapestry of loops, then its history is the story of that tapestry being woven. Spin foams provide the language for that story. To understand them, we must first revisit the spin networks of loop quantum gravity. Picture a spin network as a snapshot of space at a single instant, a graph where the links represent quanta of area and the nodes represent quanta of volume. This is a frozen moment, but reality is not a snapshot, it is a movie. A spin foam is what happens when you stack these snapshots together and let them evolve. It is a two-dimensional surface, a complex foam-like structure that interpolates between one spin network and another. Each face of the foam carries a quantum of area, and each bubble carries a quantum of volume, but now they trace out a history through a higher dimensional spacetime. The spin foam is not sitting in time, it is time, or at least, it is the quantum history of geometry. The grand ambition is to perform a sum over all possible spin foams that could connect an initial spin network to a final one. This is the gravitational path integral, a direct analog to the sum over histories approach Richard Feynman invented for quantum particles. In Feynman's famous work, a particle like an electron does not take a single path from point A to point B. Instead, it simultaneously explores every conceivable path, and we calculate its behavior by summing the contributions from all those histories. Spin foam theory applies this breathtaking idea to the fabric of reality itself. We are not summing over paths of a particle, but over all possible histories of spacetime geometry. The spin foam is the gravitational version of a Feynman diagram. Each unique foam configuration, with its specific arrangement of faces and bubbles, represents one possible quantum leap of the universe's geometry. The true quantum dynamics of gravity should emerge from the sum of all these possibilities, each weighted by a quantum amplitude that depends on the foam's intricate structure. It is a vision where the universe's past is not a single, determined thread, but a shimmering superposition of every possible way spacetime could have woven itself together to reach the present moment. Yet this magnificent vision faces a monumental challenge, the recovery problem. How do we ensure that when we sum over these wild quantum histories, the average classical behavior that emerges is the smooth, curved spacetime described by Einstein's general relativity? It is like trying to prove that the average of a trillion chaotic brushstrokes will inevitably produce the Mona Lisa. The spin foam sum must contain, within its infinite complexity, a strong peak around configurations that correspond to classical solutions of Einstein's equations. Physicists must find the right formula for the quantum amplitudes, the right weights for each foam to make this miracle happen. It is an active and difficult frontier, requiring deep insights from mathematics and computational brute force. The spin foam approach dares to treat the history of the cosmos as a quantum object in its own right, asking us to accept that the stage upon which we live is the statistical average of a frothing quantum sea of geometric possibilities. What feels like a single, solid past may be the echo of a billion histories, all equally real. The shimmering superposition of every possible spacetime history leads to a staggering question about string theory itself. If its mathematics can describe so many potential realities, how do we find our own? The answer may lie in a cosmic map divided into two vast and mysterious regions, the landscape and the swampland. First, consider the landscape. This is not a physical place, but a metaphorical terrain of unimaginable size, representing every possible stable solution of string theory. Each point in this landscape corresponds to a specific way for the extra dimensions to curl up, determining the values of fundamental constants like the strength of gravity or the mass of the electron. The number of these distinct vacuum states is beyond astronomical, estimated at 10 to the power of 500 or more. This is a 1 followed by 500 zeros, a number so vast it dwarfs the count of atoms in our observable universe. Each vacuum is a potential universe with its own unique laws of physics. In this picture, our cosmos is just one bubble in an infinite, frothing multiverse. This landscape provides a controversial but compelling framework for the cosmological constant problem. Why is the energy of our vacuum so precisely tuned to allow for galaxies and life? The anthropic principle offers an answer. In a multiverse where every possible constant is realized somewhere, we inevitably find ourselves in one of the rare, hospitable universes where the numbers allow for complexity. We are not here because the universe was fine-tuned for us. We are here because in a landscape of infinite possibilities, a universe like ours had to exist somewhere. It is a statistical selection effect, not a design. Yet, for many physicists, this feels like a retreat from explanation. Is the landscape a profound feature of reality, or a mathematical labyrinth where any observation can be explained away? This discomfort leads to the opposite concept, the swampland. If the landscape contains all possible consistent universes in string theory, the swampland is everything outside it. These are effective field theories that look perfectly sensible at low energies but cannot be completed into a full theory of quantum gravity. They are mathematical mirages, theories that seem plausible but are ultimately inconsistent with the deeper principles of a unified reality. A series of swampland conjectures act as filters, offering criteria to distinguish the landscape from the swamp. One famous example is the distance conjecture. It suggests that as you move infinitely far in field space within a consistent theory, an infinite tower of new particles must become light, effectively preventing you from ever reaching that point. Another is the de Sitter conjecture, which casts doubt on the possibility of long-lived, stable universes with a positive cosmological constant like our own. If true, it would mean our accelerating universe is not in a true vacuum but is metastable, destined to eventually decay. This is not just philosophy, it is a potential bridge to observation. These conjectures make testable predictions. For instance, they might imply specific relationships between the density of dark energy and the mass of new particles, or place sharp limits on how much the fundamental constants can vary over time and space. By looking for these signatures in astronomical data, we could empirically rule out vast swaths of the landscape or confirm that our universe sits firmly within it. The search is not just for our universe's laws, but for the very rules that define which laws are even possible. Are we living in a rare garden in a vast cosmic landscape, or is our universe one of the few stable islands in a sea of mathematical impossibility? The landscape of possible universes is a dizzying abstraction, but the challenge of quantum gravity also strikes at the very first moments of our own cosmic story. This is the trans-Planckian problem, a deep crack in our understanding of the Big Bang. Picture the infant universe during its period of hyper-fast inflation, a trillionth of a second after the beginning. Quantum fluctuations in the fabric of spacetime were being stretched by this explosive expansion, ballooning from microscopic seeds to become the vast cosmic structures we see today, galaxies and clusters of galaxies. Here lies the paradox. To produce the patterns we observe in the sky, these fluctuations must have started with wavelengths far, far shorter than the Planck length, the scale at which our classical notions of space and time are believed to break down entirely. We are using Einstein's theory of smooth spacetime to describe processes that occurred in a realm where that very theory is supposed to be invalid. It is like using the rules of continental plate tectonics to describe the jittering of a single atom. We are extrapolating our physics into a domain where we have no right to trust it, yet somehow it gives us the right answer. Where did these ultra-short wavelength modes truly come from? A theory of quantum gravity must provide the correct starting conditions for the universe, describing the physics at those trans-Planckian energies. Without it, the spectacular success of inflationary cosmology rests on a foundation we cannot see or describe. It is a cosmic credit drawn against a bank account whose rules we do not know. Confronted by energies too high to reach and scales too small to see, physicists have devised a brilliant workaround. If we cannot study quantum gravity in the early universe or near a black hole, perhaps we can build a scaled-down analog in the laboratory. This is the promise of analog gravity. The core insight is stunningly simple. The equations that describe how waves move in certain exotic fluids bear a striking mathematical resemblance to the equations describing how light moves in the curved spacetime around a black hole. By mastering one system, we can test ideas about the other. The most famous example is the sonic black hole or dumb hole. Imagine a fluid flowing faster than the speed of sound in that fluid. Now send a sound wave against the current. If the fluid is moving too swiftly, the sound wave cannot make headway. It is trapped, just like light cannot escape from a gravitational event horizon. That point of no return for sound is an acoustic horizon. In a groundbreaking experiment, researchers created such a horizon in a supercold state of matter called a Bose-Einstein condensate. And there, they detected it, the analog of Hawking radiation. Just as a black hole should emit a faint thermal glow of particles due to quantum effects at its horizon, the sonic black hole emitted a thermal spectrum of sound waves, phonons, from its acoustic horizon. This was not a direct observation of gravitational Hawking radiation, but a magnificent proof of concept. The underlying quantum process that generates radiation from a horizon appears to be universal. It depends on the geometry of the horizon itself, not on the specific force that creates it, whether it is gravity or a fluid flow. These analog models are more than just clever demonstrations. They are functional testing grounds for the strange physics of quantum fields in curved space. Scientists can manipulate the fluid flow, change its properties, and observe how the analog Hawking radiation responds. They can probe questions that are purely theoretical in the astrophysical context. What happens if you try to send a signal across the horizon? How does the information encoded in the radiation relate to what fell in? By studying these controllable systems, we gather crucial clues about the behavior of real event horizons. Analog gravity turns abstract, untouchable concepts into phenomena we can measure on a lab bench. It provides a rare experimental handle on problems like the firewall paradox and the nature of quantum information. While it may not deliver the final equations of quantum gravity, it illuminates the path by showing us which mathematical features are essential and which are mere details. The roar of a waterfall and the silence of a black hole are connected by a deep and beautiful symmetry in the laws of nature. The roar of a waterfall and the silence of a black hole share a deep symmetry, but the analogy runs even deeper. Spacetime itself might be a kind of collective phenomenon, a cosmic mirage emerging from the frantic dance of countless quantum components. This is the radical vision of quantum gravity in condensed matter systems. To grasp it, think of a flowing river. You can describe its currents and whirlpools perfectly using the smooth equations of fluid dynamics without ever mentioning a single water molecule. The fluid is an emergent reality born from the collective behavior of trillions of molecules. Now take a quantum leap. What if the smooth geometry of spacetime and the force of gravity are like that river? What if they are not fundamental, but emerge from the collective behavior of a vast, unseen quantum system? This approach uses the tools of condensed matter physics, the study of complex systems with many interacting parts, like superconductors or exotic magnets. Here, physicists search for models where familiar concepts of geometry and gravity bubble up from purely quantum information theoretic principles. One of the most startling examples is the Sachdev-Yekiteev model, or the SYK model. It describes a soup of randomly interacting quantum particles, a chaotic mess with no obvious spatial structure. Yet, when you solve its equations, something miraculous happens. This formless quantum soup exhibits properties eerily similar to a black hole in a two-dimensional universe. It has the same scrambling of information, the same thermal behavior, and crucially, it saturates the fundamental quantum limit for chaos. The SYK model is a hologram in miniature, a quantum system without gravity that nonetheless encodes gravitational physics. It suggests that the mysterious link between quantum chaos and black holes is not a coincidence but a fundamental clue. Geometry might be the language that emerges when quantum information is maximally scrambled and entangled. To see how, we must look at quantum criticality. In certain exotic materials, right at the tipping point between two quantum phases, like a magnet and a non-magnet, the system becomes scale invariant. It looks the same at every magnification, and its quantum fluctuations become highly entangled over vast distances. At this critical point, the system's behavior is often described by a conformal field theory, the very same kind of theory that lives on the boundary of a holographic universe. Studying these real-world critical points gives physicists a tangible laboratory to understand how collective quantum entanglement can give rise to emergent, classical descriptions that look like spacetime. This brings us to the architecture of entanglement itself, tensor networks. These are powerful diagrams that represent the complex web of quantum connections in a many-body system. Simple, regular tensor networks can build up a lattice that resembles a discrete version of empty space. More complex holographic tensor networks, like the ones proposed by physicists such as Brian Swingle, directly mimic the geometry of anti-de Sitter space. In these networks, the amount of entanglement between different parts of the quantum system directly corresponds to geometric properties like area and distance. More entanglement literally means a shorter emergent distance between 2 points. It is a breathtakingly concrete realization of the idea that space is not a container for relationships, but is woven from those relationships. The distance between you and the stars may not be a pre-existing void, but a measure of how quantum information between here and there is organized. These approaches transform the quest for quantum gravity from a search for exotic particles or hidden dimensions into a study of organization and information. They ask, what are the universal patterns of quantum entanglement that inevitably give rise to something that looks like a universe with gravity? The answer may not be written in the stars, but in the shared mathematical heartbeat of black holes and strange metals on the brink of transformation. The idea that distance is woven from entanglement brings us back to the most violent forge of these quantum threads, the black hole. And here, a single question has ignited decades of debate: the black hole information paradox. It began with Stephen Hawking's revolutionary calculation in the 1970s. He showed that black holes are not truly black. Due to quantum effects at the event horizon, they glow with a faint thermal radiation, slowly evaporating over eons until they vanish completely. This Hawking radiation, however, presented a catastrophic problem. The radiation Hawking initially described was purely thermal, like the glow from a hot stove. It contained no information about the specific star, spaceship, or book that had fallen in. When the black hole finally evaporates, all that intricate quantum information about what created it and what fell into it would be lost forever. This violates a sacred principle of quantum mechanics called unitarity, which states that information can never be destroyed. It can be scrambled, hidden, or transformed, but it must, in principle, be recoverable. If Hawking was right, the universe has a built-in shredder, and the foundation of quantum theory is wrong. This paradox set the stage for a war of ideas. One side argued information is truly lost, forcing a rewrite of physics. The other side, guided by the holographic principle, insisted information must escape. But how? The answer proposed by Gerard T. Hooft and Leonard Susskind is a masterpiece of quantum logic called black hole complementarity. It asks us to accept a reality that seems impossible from our classical perspective. Complementarity suggests that the information is not lost, but it is also not in two places at once in a way any single observer can witness. From the perspective of an external observer watching from a safe distance, the information from an object falling into the black hole is not lost behind the horizon. Instead, it is scrambled and encoded into the Hawking radiation that leaks out over the black hole's immense lifetime. The infalling object is effectively reflected at the horizon, its information imprinted on the radiation. But from the perspective of the object itself, or an astronaut foolishly riding it in, nothing special happens at the horizon. They cross it smoothly according to Einstein's equivalence principle, carrying their information intact into the black hole's interior. Both stories are true, but they are complementary descriptions, like the wave and particle nature of light. Crucially, no single observer can ever see both copies of the information to prove a contradiction. To do so would require an experiment that combines data from inside and outside the horizon, which is fundamentally impossible. Any probe sent to retrieve the information from the interior would be stretched and compressed by tidal forces or require impossible energies long before it could report back to the outside. The two realities, the burning hologram and the smooth spacetime, are mutually exclusive perspectives of a single quantum system. They cannot be combined into one classical picture because that would violate the quantum limits on what can be known. Black hole complementarity is not a comfortable idea. It forces us to abandon the notion of a single, objective reality that all observers share. Instead, reality becomes observer-dependent, a tapestry of consistent but exclusive viewpoints. The fate of information, and perhaps the nature of existence itself, depends on where you stand. Black holes are not just cosmic vacuums, they are cosmic thermometers. Stephen Hawking's greatest insight revealed that a black hole must have a temperature, and therefore, like any hot object, it must possess entropy. Entropy is a measure of disorder, of hidden information. Jacob Bekenstein first proposed the idea, and Hawking cemented it with a formula of breathtaking simplicity. The entropy of a black hole, S, is equal to 1/4 of the area of its event horizon measured in Planck units. S equals are divided by 4. This is the Bekenstein-Hawking formula. It is a bridge between the worlds of gravity and quantum mechanics, written in the geometry of spacetime itself. The area of the horizon, a purely gravitational feature, determines the amount of quantum information the black hole can hide. But this formula was a revelation waiting for an explanation. If entropy is a measure of hidden microscopic states, what are those states for a black hole? What are the individual quantum building blocks whose countless configurations give rise to that smooth classical horizon? For decades, the formula stood as a profound clue without a mechanism. Then, in 1996, string theory delivered a stunning answer. Physicists Andrew Strominger and Kamran Vafa performed a calculation of breathtaking precision. They considered a specific extremal black hole in a universe with extra dimensions, a configuration where the gravitational pull is perfectly balanced by other forces. Using the tools of string theory, specifically D-branes, which are multidimensional surfaces where strings can end, they counted the number of distinct quantum mechanical ways to arrange the strings and branes that could make up that black hole's mass and charge. They were counting the black hole's possible microstates. The result was not an approximation. It was an exact match. The logarithm of the number of microscopic configurations they counted gave an entropy that precisely equaled the Bekenstein-Hawking formula, 1/4 of the horizon area. It was a watershed moment. For the first time, a theory of quantum gravity had not just postulated a property of black holes. It had derived it from first principles, from counting the fundamental quantum degrees of freedom. This success was not limited to string theory. Loop quantum gravity also rose to the challenge. In that framework, the event horizon is pierced by the quantized lines of a spin network. Each puncture contributes a tiny bit of area, and the different quantum numbers associated with those punctures represent different microstates. When physicists counted the number of ways these lines could puncture the horizon without changing its total area, they too found a result that beautifully reproduced the Bekenstein-Hawking entropy. Two radically different approaches, one based on vibrating strings in extra dimensions, the other on woven loops of space, both arrived at the same destination. They both showed that the vast entropy of a black hole emerges from the astronomical number of ways its quantum constituents can be arranged, just as the entropy of a gas emerges from the countless positions and velocities of its molecules. This microstate counting is more than a technical triumph. It is a powerful validation that these theories are touching something real. They are not just elegant mathematics, they are providing a microscopic anatomy for the most enigmatic objects in the cosmos. The smooth, dark surface of a black hole is not featureless. It is the calm face of a maelstrom of quantum possibility, a statistical average over a near-infinite number of hidden configurations. The next time you picture a black hole, do not see a simple dark sphere. See a library. Its impenetrable cover is the event horizon, and its unimaginable content, written in the language of strings or loops, is every story that ever fell in. The Bekenstein-Hawking formula is the library's catalog number, and quantum gravity is finally teaching us how to read the books. The library of a black hole's microstates is vast, but it is still a finite collection of information. This finiteness points toward a deeper truth about our entire cosmic story. If we step back to view the universe as a whole, we are immediately confronted by a dizzying, perhaps meaningless infinity. An infinite universe would contain an infinite number of identical copies of you, me, and every possible variation of our lives in an endless sea of cosmic patches. This is the measure problem of cosmology, and it renders probability and prediction virtually impossible. How can we say anything is likely or unlikely if every conceivable event happens an infinite number of times? Raphael Bousso's causal patch cosmology offers a profound and humbling escape from this infinite maze. It suggests that the only physics that is truly meaningful, the only physics we can ever claim to describe, is not that of the entire universe but of our own observable horizon. A causal patch is the finite region of spacetime that can ever be in communication with a single observer. It is the ultimate bubble of relevance bounded by our past light cone and our future horizon. Nothing outside this patch can ever affect us, signal us, or be measured by us. In this view, the quest for a final theory of quantum gravity shifts dramatically. We should not seek equations that describe the whole of an infinite, unknowable multiverse. Instead, the ultimate theory might only describe the quantum state of a single causal patch. It is a theory of what one observer can see and measure, a cosmic autobiography rather than a universal history. This connects cosmology directly to the heart of quantum mechanics itself, the measurement problem. In quantum theory, a system does not settle into a definite state until it is observed. Causal patch cosmology extends this principle to the grandest scale. The universe as a whole may exist in a blurred quantum superposition of every possible history and geometry, but within each causal patch, for the observer at its center, a specific classical reality crystallizes through a cascade of quantum measurements. Your observations, from detecting a photon from a distant galaxy to noticing the fall of a leaf, are not just recording reality, they are continuously selecting one thread from the quantum tapestry of the whole. This leads to a fascinating concept, the cosmic census. If the fundamental description of reality is tied to a single patch, then the constants of nature and even the very laws of physics we measure might not be universal, absolute truths. They could be environmental variables unique to our particular patch, determined by the specific way our quantum observations have resolved the wave function of our local cosmos. Other causal patches in the far-flung reaches of the multiverse could have settled into different classical configurations with different constants. We are not reading the master blueprint of creation. We are reading the architectural plans for our own finite room in an infinite mansion. This framework elegantly avoids the paradoxes of infinities by accepting a fundamental limit to knowledge. The final theory would not be a set of equations painted across the sky, but a rulebook for how a single conscious perspective emerges from and interacts with the quantum whole. It asks us to consider that the universe is not a pre-recorded movie playing on a giant screen. It is a live performance, and the act of watching is what brings each scene into being. Are the laws of physics less like eternal commandments and more like the local customs of our tiny, illuminated corner of existence? Our cosmic autobiography begins with a question that seems to defy logic. How did the universe start from nothing? Quantum cosmology offers two profoundly different creation stories, each written in the language of the universe's own wave function. The first is the no-boundary proposal crafted by James Hartle and Stephen Hawking. It asks us to let go of the idea of a singular beginning, a first moment in time. Instead, they propose that if we could rewind the cosmos to its earliest state, time itself would lose its sharp, distinct character and become more like a dimension of space. In their mathematical vision, the universe's wave function is calculated by summing over all possible compact, smooth four-dimensional geometries that have no edge, no boundary in the past. The classic analogy is the surface of the Earth. If you travel north, you eventually reach the North Pole. But what is north of the North Pole? The question loses its meaning because the pole is not an edge, it is just a point on a smooth, closed surface. In the same way, the Hartle-Hawking state describes a universe that is finite in extent but has no boundary, no singular starting wall. The Big Bang is not an explosion from a point, but a smooth, rounded origin where time emerges naturally from geometry, like moving south from the North Pole. This no-boundary wave function predicts a universe that starts in a specific, most probable configuration, one that naturally leads to a long and robust period of inflationary expansion. It favors a universe that is large, flat, and uniform, much like the one we observe. The initial conditions are not arbitrary, they are the most likely outcome of this quantum smoothing process. Yet another giant of theoretical physics, Alexander Vilenkin, looked at the same quantum equations and saw a very different genesis. His is the tunneling proposal. In this picture, the universe really did come from nothing, not even space or time, but it did so through a quantum process we know from subatomic physics. In radioactive decay, an alpha particle is trapped inside an atomic nucleus by an energy barrier. According to classical physics, it lacks the energy to escape. But quantum mechanics allows it to tunnel through that barrier, appearing on the other side as if by magic. Vilenkin applied this logic to the cosmos itself. He envisioned a state of nothingness, a perfect vacuum with zero size as one side of a barrier. On the other side is an expanding universe, even a tiny one. Quantum mechanics allows the entire cosmos to tunnel from nothing into something. This is not a causal process in time, because time does not exist on the nothing side. It is a spontaneous quantum birth. The emotional tone of these two proposals is strikingly different. The Hartle-Hawking no-boundary state feels like a gentle, inevitable rounding off of reality. Vilenkin's tunneling feels like a dramatic, improbable leap into existence. This leads to a crucial mathematical difference. The no-boundary wave function is largest for a universe that starts with the smallest possible rate of expansion, which then inflates. The tunneling wave function, however, is largest for a universe that starts with a high expansion rate. This means the two proposals predict different likelihoods for various initial conditions for inflation. One favors a slower start, the other a more explosive one. While both describe a quantum origin without a singularity, they offer competing visions of probability at the dawn of everything. Was our universe the most likely smooth geometry, or a spectacularly lucky quantum jump? The answer, hidden in the faint patterns of the cosmic microwave background, might one day tell us which creation story is written into the fabric of reality. The smooth, rounded origin of the Hartle-Hawking state offers a profound escape from the most terrifying predictions of Einstein's equations. Those equations, in their pure classical form, inevitably lead to places where reality itself breaks down, the singularities. At the heart of a black hole and at the beginning of the Big Bang, the mathematics screams infinity. Density becomes infinite, curvature becomes infinite, and our trusted laws of physics dissolve into nonsense. For any theory of quantum gravity to be taken seriously, it must face these monsters and tame them. It must tell us what truly happens when spacetime is pushed to its absolute limit. This is not a side quest, it is the central drama. Resolving singularities is the ultimate test, a proving ground that separates mathematical speculation from a true description of reality. Each major approach wages this battle in its own way. Loop quantum gravity confronts the Big Bang head-on with its vision of a quantized geometry. In this framework, space cannot be squeezed to an infinitely small point because there is a smallest possible volume, a fundamental quantum of space. As you rewind the cosmos toward the classical singularity, these quantum properties of geometry become dominant. Instead of an infinite collapse, the gravitational field becomes powerfully repulsive at these tiny scales. The collapse of a previous cosmic phase halts and reverses. The Big Bang was not a beginning from nothing, but a big bounce from a prior era of contraction. Our universe's hot, dense birth was a moment of transition, a cosmic rebound in an eternal cycle. Inside black holes, a similar repulsion is predicted to occur, preventing the formation of a point-like singularity and potentially leading to a bridge to another region of spacetime. The terrifying infinite pit is replaced by a quantum tunnel. String theory approaches the problem with a different, equally elegant toolkit. It softens the singularities by replacing point particles with extended, vibrating strings. When a string probes a region of extreme curvature, it does not see a sharp mathematical point. It smears itself out over a finite area, blurring the violent infinities away. For the Big Bang, string theory often frames the event not as a singular beginning, but as a dramatic transition between different vacuum states in the vast landscape of possibilities. Our universe could have nucleated from a collision of higher dimensional brains or tunneled from a previous vacuum with different physical laws. The singularity is replaced by a process, a quantum leap from one stable configuration of the extra dimensions to another. The question shifts from what happened at a point to how the geometry of hidden dimensions rearranged itself. Other frameworks offer their own resolutions. Causal-set theory, with its discrete events, simply has no place for a continuum where an infinity can occur. The universe is a finite, if immense, collection of causal links. Non-commutative geometry introduces a fundamental fuzziness to spacetime, so that the closer you try to look at a point, the more uncertain its location becomes, preventing the sharp, singular pinpoint from ever forming. Even the asymptotic safety program aims to show that the strength of gravity's quantum interactions remains finite at all energies, ensuring that the equations describing the universe's birth or a black hole's core never produce infinite answers. The shared ambition is clear: to erase the infinities and restore sense to the cosmos. A successful theory must provide a complete, finite picture of these extreme events. It must tell us what preceded our universe's expansion and what lies beyond the event horizon of a black hole. The removal of singularities is more than a technical fix, it is a philosophical necessity. It promises a universe that is rational and complete at every scale, with no room for places where the rules simply give up. When we finally have the equations of quantum gravity in hand, we will look at the Big Bang not as a wall at the beginning of time, but as a window into a deeper, more coherent reality. The equations of quantum gravity are not just beautiful abstractions, they are predictions waiting to be proven wrong. The wildest ideas must eventually face the cold, hard judgment of experiment. So how do we test theories about the fabric of reality itself? We look for the tiny cracks where the quantum nature of gravity might leak into our classical world. One of the most promising avenues is the music of colliding black holes, gravitational waves. When two massive objects spiral together and merge, they send ripples through spacetime. Our detectors, LIGO and Virgo, have already captured this cosmic symphony. But what if the event horizon is not the perfectly smooth membrane of classical relativity? Theories like loop quantum gravity or firewalls predict that the horizon might have a quantum structure, a fuzziness, or a reflective property. This could cause faint echoes in the gravitational wave signal, a subtle series of whispers following the main crash. Current detectors are not yet sensitive enough to hear these whispers definitively, but next-generation observatories in space, like LISA, will listen with far more acute ears. They will scan the aftermath of mergers for any anomaly, any signature that the horizon is not what Einstein predicted. Another cosmic messenger holds clues from the very beginning. The cosmic microwave background, the ancient afterglow of the Big Bang, is imprinted with faint patterns of polarization. Certain modes of this polarization, called B modes, could be the smoking gun for primordial gravitational waves, ripples generated during the universe's explosive inflationary expansion. Experiments like BICEP and the Keck array at the South Pole are staring at this frozen light, searching for this specific curl in its polarization. Finding it would not only confirm inflation but could also reveal the energy scale at which it happened. That scale is tantalizingly close to the Planck energy, the realm of quantum gravity. The specific pattern of those B modes could carry imprints of the quantum gravitational laws that govern the universe's first fleeting moments. Could the signature of vibrating strings or quantum loops be written in the sky's oldest light? We can also push matter to its limits. The Large Hadron Collider smashes protons together at energies that recreate conditions a fraction of a second after the Big Bang. While it operates far below the Planck scale, some theories predict subtle effects that could appear. Extra dimensions, as required by string theory, could reveal themselves through missing energy as particles momentarily travel into these hidden realms. Microscopic black holes, though considered a long shot, would be an unmistakable sign of new physics involving gravity at tiny scales. So far, the LHC has found no such evidence, placing stringent limits on these possibilities and forcing theorists to refine their models. Perhaps the most ingenious tests, however, happen not in giant colliders or vast observatories, but on quiet lab benches. Tabletop experiments search for the granularity of spacetime itself. If spacetime is a quantum foam, as many theories suggest, then light traveling over long distances might experience a subtle blurring, a loss of sharpness in distant astronomical images. Others look for violations of Lorentz invariance, the principle that the speed of light is constant for all observers. If time and space split at high energies, as in Horava-Lifshitz gravity, there might be tiny, direction-dependent variations in the speed of light for different colors. Exquisitely sensitive atomic clocks and laser interferometers can now search for these effects. Some experiments even use superconducting circuits to create analog black holes, testing the universality of Hawking radiation in a controlled setting. Each of these paths, from the echoes of black hole collisions to the frozen light of creation and the precision of human-made instruments, forms a net slowly tightening around the truth. The theories we have explored are magnificent stories, but they are not all true. Data is the final arbiter, the cosmic judge that will one day point to a single, breathtaking narrative and consign the others to history. Our greatest discovery will not be which theory is the most elegant, but which one matches the silent testimony of the universe itself. The search for quantum gravity has led us from the tiniest loops of space to the echoes of black holes. But one final, breathtaking possibility remains, a theory that is not about our universe alone, but about all possible universes. This is the multiverse, and it may be the ultimate consequence of our quest. It emerges from three powerful streams of thought, each pointing toward a cosmos of unimaginable plurality. The first is eternal inflation. Picture the explosive expansion of the Big Bang not as a one-time event, but as an endless, bubbling process. In this view, our entire observable cosmos is just one bubble that nucleated in an eternally inflating background. New bubbles are constantly forming, each with its own random set of physical constants and laws. We live in one where the numbers allow for atoms, stars, and life, but an infinity of other bubbles exist where physics is utterly alien. The second stream flows from string theory's vast landscape. With its 10 to the power of 500 or more possible vacuum states, string theory does not predict one universe. It predicts a near infinity of them. Each stable configuration of the extra dimensions defines a different universe with different particles and forces. Our universe is simply one address in this cosmic megacity. The third stream comes from the very heart of quantum mechanics itself, the many worlds interpretation. In this view, every quantum decision, every particle's choice between one spin and another, does not collapse into a single reality. Instead, the universe splits, branching into parallel worlds where every possible outcome actually happens. Over eons, this ceaseless branching creates a multiverse of staggering diversity, all stemming from the same quantum roots. These three ideas, born in different fields, converge on a single, radical conclusion. Reality is not a single story. It is a library containing every book that can be written according to the meta-laws of physics. This forces us to ask a profound question about quantum gravity. Is its purpose to describe our single, unique universe, or is it meant to provide the framework, the mathematical grammar, for the entire multiverse? If the latter is true, then the ultimate theory may not be a unique set of equations that spit out our specific cosmos. Instead, it might be a rulebook for generating possibilities, a cosmic algorithm that defines the landscape of all logically consistent universes. Our particular home, with its specific mass for the electron and strength for gravity, would then be just one possible output, one island in a sea of mathematical potential. This shifts the goal of physics in a fundamental way. We may not find a theory that says why the cosmological constant has the precise, tiny value it does. We may find a theory that shows how such a value is possible and why, in a vast multiverse, some bubbles inevitably end up with it. The quest becomes not for the one true story, but for the rules that govern the library itself. Does this mean the search for a final answer is futile? Not at all. It means the answer might be more profound than we imagined. The Holy Grail would be a single, elegant mathematical structure, perhaps M-theory, or a complete formulation of quantum gravity that is so self-contained it necessarily contains all possible physical realities within it. Our universe's specific laws would be local by laws, while the master law describes the entire multiversal continuum. This framework could finally resolve puzzles like the fine-tuning of constants through the anthropic principle, not as a surrender, but as a natural consequence of a cosmos too large for uniqueness. As we stand at the edge of this final theory, we must wonder, are we discovering the blueprint for a singular creation, or are we deciphering the constitution of all existence? The answer will tell us whether we are citizens of one universe or momentary visitors in a reality without end. From the loops of space to the echoes of black holes, we have journeyed through 30 distinct visions of reality. Each one is a testament to human curiosity, a different path through the same uncharted wilderness. The quest to weave quantum mechanics and gravity into a single, seamless tapestry is more than a technical puzzle. It is the greatest intellectual adventure of our time, a journey that forces us to confront the very nature of time, space, and existence. Does time truly flow, or is it an emergent story we tell ourselves? Is space a fundamental stage, or a magnificent illusion woven from quantum entanglement? The answers we seek will rewrite not just our physics textbooks, but our deepest understanding of what it means to be, and to be here in this cosmos. Now we turn the question to you. Which of these theories captures your imagination the most? Does the holographic principle bend your mind, or does the elegant simplicity of asymptotic safety appeal to you? Share your thoughts in the comments below. Let us know which cosmic blueprint you find most compelling. This story is far from over. The next chapter is being written right now, in the data streaming from gravitational wave observatories, in the precise maps of the cosmic microwave background, and in the quiet hum of particle colliders pushing matter to its limits. Future telescopes, like the Roman Space Telescope or the gravitational wave detector LISA, will open entirely new windows onto these mysteries. With every new observation, the universe whispers more of its secrets. One day, perhaps sooner than we think, a brilliant mind or a crucial piece of data will guide us to the truth. That truth will be stranger and more beautiful than any of us can currently imagine. If you want to be there for that discovery, to explore the next layer of cosmic mystery with us, make sure to subscribe. Our journey into the heart of reality has only just begun.